In this lesson, we will discuss Ohm's law and work a few simple problems involving its application. Again, it is not all-inclusive of everything we need to know on the subject matter to complete this course. Additional information on Ohm's law can be found in the General Aviation Maintenance Technician's Handbook, FAA Publication H-8083-30, and in Advisory Circular 4313. Before we begin our discussion on Ohm's law, let's review three properties of an electrical circuit involved in the analogy between an electrical circuit and water flow. Here we see a drawing of a water tank with a pipe at the bottom. The pressure at the bottom of the tank is analogous to voltage. Voltage does not flow, but is measured at a point like the pressure at the bottom of the tank. The voltage pressure instead is what drives the electrons through the circuit. Water pressure forces the water through the pipe in this example. The more water pressure, the more water that flows through the pipe. Similarly, the more voltage pressure, the greater the electrical current or flow of electrons through a conducting wire. The pipe in the water example is analogous to the conducting wire in an electrical circuit, and the smaller the pipe, the more resistance to the flow of water. Likewise, the smaller an electrical wire, the more resistance to the flow of electrons in a circuit. In addition to the size of the conducting wire, though, most everything else in the electrical circuit offers some resistance. Purpose-built resistors increase the resistance, as do items such as light bulbs, electric motors, etc. Ohm's law states that the current in a circuit is proportional to the voltage and inversely related to the resistance. Or written as an algebraic expression, the voltage equals the current times the resistance. Or we can say that the current equals the voltage divided by the resistance. Or we can say that the resistance is equal to the voltage divided by the current. Pictured here, you will see a few of the electrical symbols you will need to know for this course. A battery, a conducting wire, a resistor, a light bulb or some other load, an open and closed switch, and a ground. There are, however, literally hundreds of electrical symbols we will work with as an aviation maintenance technician. Many of them you can find in Advisory Circular 4313. Here is a simple Ohm's law example showing the relationship between voltage, current, and resistance. Can we use Ohm's law to determine how much current will flow through a circuit powered by a 4-volt battery with a 2-ohm resistor? Ohm's law tells us that voltage equals current times resistance. Therefore, current must equal voltage divided by resistance. Thus, our current in this circuit equals 4 volts divided by 2 ohms equals 2 amps. In this example, what voltage is required to produce 2 amps of current through a circuit with a 3-ohm resistor? Our voltage equals our current times our resistance. Therefore, since our voltage equals 2 amps times 3 ohms, or 6 volts. What resistance is required to limit the current to 4 amps if a 12-volt battery is in the circuit? Referring to Ohm's law, we know that resistance equals voltage divided by current. Therefore, the resistance equals 12 volts divided by 4 amps equals 3 ohms. Resistances in series sum together when calculating total resistance. Resistors are considered to be in a series when there are no junctions or branches between them. The same current will flow through each resistor in a series. What is the current in the circuit below? Since the resistors pictured in this schematic are in series, the total resistance in this circuit equals 2 ohms plus 4 ohms, or 6 ohms. To find the total current flow in this circuit, current flow equals voltage divided by resistance, or current flow equals 12 volts divided by 6 ohms, or 2 amps. Remember, resistances in series sum together when calculating total resistance. What is the resistance of the light bulb in this schematic? Our total resistance equals our voltage divided by our current, and our total resistance then equals 12 volts divided by 4 amps, or 3 ohms. If the total resistance equals 3 ohms and the value of one of the two resistors given as 2 ohms, then the remaining resistor must equal 1 ohm. Kirchhoff's law of voltages informs us that the sum of all of the voltage drops in a circuit is equal to 0. If we consider the source voltage to be positive, there will be a negative voltage drop across each resistor. The voltage drop across each resistor can be calculated with Ohm's law. If we have 2 amps of current flowing through a 4 ohm resistor, then 2 amps times 4 ohms equals 8 volts that must drop across that resistor. Similarly, if we have 2 amps of current that flows across a 2 ohm resistor, there will be 4 volts that drop across that resistor. We have 8 volts drop across the first resistor and 4 volts drop across the second resistor. We then have 12 volts that have dropped throughout this circuit powered by a 12-volt battery, confirming Kirchhoff's law. In this example, let's calculate the total current flow and the voltage drop across each resistor. Then, relative to point D, let's find the voltage at points A, B, and C. We begin to find the total current flow by first finding the total resistance. 3 ohms plus 4 ohms plus 1 ohm equals 8 ohms. Then using Ohm's law, we have total current equals 24 volts divided by 8 ohms equals 3 amps. We can then determine the voltage drop across each resistor by multiplying the resistance of each resistor by the current flowing through it. 3 amps times 3 ohms equals 9 volts that drop across the first resistor. 3 amps times 4 ohms equals 12 volts that drop across the second resistor. And 3 amps times 1 ohm equals 3 volts that drop across the third resistor. The voltage at point A will be 24 volts as the voltage has not dropped yet. The voltage at point B will be 15 volts because 9 volts dropped at the first resistor. And subtracting that from the 24 voltage source leaves 15 volts. We drop 15 volts across the first resistor and 12 volts across the second resistor because 3 amps times 4 ohms equals 12 volts. That leaves 24 minus 9 minus 12, or 3 volts at C. We drop the last 3 volts across the third resistor for a total of 24 volts.